Hello and welcome. Today we're going to dive deep into something truly fascinating, the very nervous system of a modern robot. We're talking about ROS1.
But before we begin, let me ask you a question. Just picture a complex robot, with a gripper, multiple cameras, wheels, dozens and dozens of sensors. How do all of these parts, maybe thousands of components, all talk to each other? How do they coordinate everything they do? Instantly, without any lag. It's a bit of a mystery, right? Well, today, we're going to solve it together.
All right, let's get started. This diagram you see here, this is our map for the journey. Now, I know it might look a little complex right now, but please don't worry about that. We are going to build this entire picture together, piece by piece, and we'll keep coming back to this map. I promise, by the end of this, you'll understand it completely.
So the answer to our mystery lies in something called ROS. Now, a lot of people think of it as the robot's operating system, the brain of the machine. But is that really the full story?
Officially, ROS stands for Robot Operating System. It's an open-source framework. Think of it like a giant toolbox designed to help developers build software applications for robots. It gives you all the libraries and tools you need to get things up and running quickly.
And here's the twist. Despite having operating system right there in the name, ROS is not actually an operating system like Linux or Windows is. It's better to think of it as a special layer of software, a framework that runs on top of a real OS. It's what adds all the special robotic capabilities that a normal operating system just doesn't have.
This little equation here breaks it down perfectly. It's really a combination of four key things. First, you've got the plumbing. This is the communication system that lets all the different parts talk to each other. Then you have the tools to help you build and debug everything. Next up are the capabilities. These are like ready-made solutions for really complex things like navigation or picking up objects. And finally, and this is so important, you have the community, a massive global network of people all sharing their work and helping each other out.
But, the first version of this system, which we call ROS1, it had a very big problem. A critical weakness, a fundamental flaw, right at its very heart.
Let's go back to our map. Take a look at the diagram on the left. This is ROS1. Do you see that purple box right in the middle, the one labeled master? I want you to think of this master as a central telephone operator for the entire robot. Every single part, every sensor, every motor had to check in with the master first just to find out how to talk to any other part.
So this leads to the most crucial point. The master node is what we call a single point of failure. What happens if your one and only telephone operator suddenly decides to go home? The entire phone network just shuts down. It's exactly the same here. If that master node fails, the robot's whole communication network collapses. Instantly, the robot is blind, deaf, and dumb.
This was the big challenge. If the master fails, the robot fails. Simple as that. So how do you build a system with no master? A system where every single part can discover and talk to every other part all on its own, instantly and reliably, without a central operator. How do you do that?
The answer, the hero of our story, is a very powerful technology called DDS. This is the new way to communicate. DDS stands for Data Distribution Service. And listen, this isn't some new experimental idea. No way. This is a battle-tested, incredibly reliable communication standard. It's the same technology used in systems where failure is simply not an option. We're talking about air traffic control, high-frequency stock trading, really complex defense systems.
Now, how does it work without a master? It's a beautiful concept. Instead of a central operator, DDS creates something called a global data space. Think of it like a shared virtual cloud, a bulletin board that all the parts of the robot can access. Data isn't sent from point A to point B through a hub, it's just placed into this shared space for anyone who needs it to see. And the way it works is brilliantly simple. A component, which we call a node, will announce or publish its data to a specific channel. We call this channel a topic. Then, any other node that needs that data simply subscribes to that same topic, and it starts getting the information instantly. It's a publish-subscribe model.
Here's a perfect, simple example of how this works. A temperature sensor doesn't need to ask a master where the cooling fan is. It just publishes its reading to a temperature topic. Meanwhile, the cooling fan controller is already listening. It's subscribed to that topic. The moment it sees the temperature is too high, it just turns on. It's simple, it's direct, and there is no master required.
So now, let's put all of these pieces together. Let's step back and look at the complete picture of our new, much improved architecture.
And here it is, our completed map. You can see at the very bottom we have that solid DDS framework. That's the robust foundation. And then sitting right on top of it is the ROS2 framework. The absolute beauty of this layered approach is that robot developers can now just focus on building their amazing applications. They don't have to worry about the complex details of how communication is happening underneath. It just works. So what's the bottom line? This table really summarizes the huge leap forward. With communication, we move from a custom system with a single point of failure to a decentralized and incredibly robust DDS system. For security, ROS1 had almost nothing. ROS2 has security built right into its core thanks to DDS. And finally, platform support. ROS1 was mainly for Linux, but ROS2 is truly cross-platform, running on Linux, Windows, and Mac OS. It is a complete upgrade in every way.
So today, we've built the robot's nervous system, a fast, reliable, decentralized network. But what good is a nervous system without a brain to process all that information and make decisions? In our next explainer, we will explore exactly that, the robot's brain, and how it handles perception, navigation, and decision-making. Hari har!